Now let's talk a little bit about the same algorithm from an analysis perspective. And I'll be only dealing with coevolution, which is something new. Combinatorial optimization is a well-known problem. So let me only and only touch upon the analysis perspective of the coevolution part of it. So let's start over with what we started off with. So fx is equal to x1 square plus 10 x1 x2 plus x2 square species 1 plus x3 square plus 20 x3 x4 plus x3 x4 square species 1 and species 2. Now, unlike the previous time, I did not tell the algorithm that these are completely independent, solve them completely independently. I just use a cooperative coevolution from this, and let's take in a representative. So my aim is to see if the algorithm can really figure out that the problems do not depend on each other and the evolution is more or less the same as to independent evolution. So let's have species 1 population. So that's x1, x2, and these are some individuals. And this is species 2 population. x3 and x4. And I have a representative. Let's say b1, b2, b3, b4. And let's calculate the fitness function value of a random individual xi from species 1. So by substitution, and let's say this is of course x1 and x2. So let's create the substituted individual. So the substituted individual, it becomes x1, x2 because of substitution, and b3 and b4 from the representative. So this is x1 square plus 10 x1 x2 plus x2 square minus plus x3 square, which is b3, now this one really doesn't matter because we'll be using ranking and this one is just a constant, but still let me write it up because I have been doing it. So b1 square plus 10 b1 b2 plus b2 square plus b3 square plus 20 b3 b4 plus b3 b4 to the power 4. For all these individuals over here, for one generation, b3, b4, b1, b2 are constants. They are constants. Constants that do not affect rank. And hence they don't affect the expectation value. So what you see is that no matter what you take as b3 and b4, b3, b4 changes, becomes large, small, keeps changing. This evolution is independent of what this representative is. So this evolution is independent. The only thing that I did was to say that x1, x2 will be here and x3, x4 will be here. And after that to say that this evolution does not depend on the value of this representative. It was calculated by the algorithm itself. So what you see is that for this problem, this evolves independently. So implies evolution of species 1 is independent of representative of species 2 and vice versa, which I'll not prove. So the evolution happens as you would expect. It happens completely independently, or a problem has been broken out to be an independent problem. So that's exactly what coevolution does, is independently evolves the two populations if there are no cooperative terms. Now let's take in another case where the population is completely dependent. And let's say I still make the error and I do x1, x2, and x3 and x4. Species 1, species 2. So that's xi1, whose fitness I will calculate it up, and then again b1 and b2 are what are my representatives. So my representatives are b1, b2, b3, b4. And let's do it quickly. So fitness of anything which is constant I will not write down. So x1 square, x2 square, x2 square, b3 square, x3 is b3, b4 square, that becomes a constant, x1 square, b4 square, x1, x2, b3, b4 plus a constant minus a constant, and this one is a constant, so it doesn't matter. So now you see that the problem is no longer independent of B3 and B4. So now is evolution of species 1 depends upon representatives of species 2, and in this case it highly depends. So evolution of species 1 highly depends upon the representative of species 2. Now what really happens is, after first generation, practically these representative will change. And these representative will change. Now imagine you did one evolution of this species and you did one evolution of this species and this representative change. Because this representative change, the fitness function is changed. Have you ever heard of an evolution where after one generation the fitness function changes because the representative of the other population has changed? Weird, unacceptable, bad, but that's exactly what will happen. So the problem here is, after first generation of species 2, representative of species 2 changes, hence the fitness function of species 1 changes, which means whatever it had done previously is not good enough. It'll have to redo it up because it was evolving, optimizing for a problem. The problem changed. And because the problem changed, now you need to do a new evolution. So this change destabilizes this, and because of that, this changes, which destabilizes this. So destabilizes is, so destabilizers is a nice evolution was happening. There was a fitness landscape, the individuals were converging, and then I shake it up, I destabilize, and I change the fitness landscape. So the first one destabilizes the other one destabilizes the first one, and hence you are now optimizing against a changing fitness function landscape. Because of reasons, the convergence will still happen, and those reasons are that sometimes a B3 will get a dominating value and it will not be possible to get a better B3 gene, so it will almost converge. That will force B4 to converge, which will eventually cause B1 and B2 to converge. So that will happen. But evolution is now a lot harder. Evolution is now not a lot more harder in contrast to what you would have done with just one fitness function value. And therefore, let us do one thing. Let us compare two types of evolution. So x1, x2, x3, x4 conventional with x1, x2 and x3, x4. In this case, what happens is they both destabilize themselves up while no such thing happens over here. So this one is better. That's why if the problems are not nearly independent and you solve it by using coevolution, you can make a mess of everything. And in the previous case, what happened was the number of fitness function evaluations over here was the number of generations times n, and here it was the number of fitness evaluations were generation times n times number of species. This is number of individuals. So it requires m times more fitness evaluation, but then of course this operates on upper bound minus lower bound raised to power 4, that's a hypervolume, and this operated on upper bound minus lower bound square twice, so this one is a lot easier. So if the populations are independent and you divide that up, it is a boon because the search space reduces dramatically and the effect of destabilization is not there. But if the population is not nearly independent and you still use coevolution, you will keep on destabilizing yourself up. You'll keep destabilizing the other one, and the number of fitness functions values are larger, and because of destabilizing, the convergence takes a lot larger time. And therefore, the limiting case is the one that I took in. So with this one only, let's calculate the fitness function value using this one. So this becomes x1 square plus 10 x1 x2 plus x2 square plus b3 square plus 20 b3 b4 plus b3 b4 4 plus 10 x1 plus 10 x1 b3, so which is equal to x1 square plus 10 x1 x2 plus x2 square plus 10 x1 b3 plus constant. Now the change of representative does cause a change in fitness function value. So the fitness function value keeps on changing. However, out of 4, out of 4 terms, only one term has also two components, out of which one is B3. So the effect is extremely small. So if B3 changes by a small value, the ranking is not going to change. Ranking is not going to change. Out of a big expression, it's one small term which is dependent on it, or the cooperative term is small. So if that's why initially I said that small term, and that's exactly what I meant, that if this term is not dominating, then the effect of change of the representative of species 2 is negligible, and therefore the population acts near independently. Sometimes initially when B3 B4 changes by a long fraction, yes, there is some destabilization, but later on when it just changes by a little value, then this entire expression is passive to a little changes in B3, because these terms will dominate. And because these terms will dominate, the population will become overly dominated by these individuals alone. And because it will become overly dominated by these individuals alone, what you would see and what you would expect is that the species are then acting almost as if they are independent parallel. And that's practically what happens. So let's take in the same example. You're solving a good project. There's a person who's good in UI, there's a person who's good in development, there's a person who's good in documentation, and all of you sit together once and sort it out. So the UI person says that 2 seconds is the limit, otherwise the UI will lag. And then the person says that, okay, algorithmic person says that I'll have to lower my precision. And the documentation guy says that you cannot use something which is not reusable because I won't be able to explain it. So people put constraints on each other. So sometimes the development guy has to change the algorithm. That's the UI guy destabilizing the development guy. Sometimes the development guy destabilizes the UI guy and says that there are more things to be taken care of. There are more features. All of them should be usable. Your UI is too simple. But later on, when this basic thing and destabilizing and initial fighting is done, the UI is independent, the development is independent, the documentation is almost independent. It's not that you really need to fight in. Similarly with the choice of sensors and actuators for the robots, initially they'll be destabilizing. The battery guy will say that I cannot give you that much of power. You lower your requirements, you lower your battery consumption, and the guy will say that, okay, I can lower down the precision level, and the developer will say is, okay, there's a redundancy, I can exploit that. So initially people will destabilize itself, where one will say that my requirements are not being fulfilled by you, and there will be fight. But then nearly more or less the battery guy will know this is my playground of work, and it's now an independent module. How do I act? It has minor effect on all the others. Yes, the little curves of the robot will change by the size of the battery. It's not going to affect much. Similarly, you want to evolve a neural network using coevolution. So what do the hidden layer neurons do? They are all feature detectors. And what does the overall network do? It tries to get the best combination of features. So initially there's a fight between the neurons to develop diversity, everybody specializing in a different area, and everybody solving at least some part of the problem. But later on, every neuron knows which area or which patterns of inputs it's concerning about. Then it could locally specialize itself within that area, within that patterns. It doesn't affect much of the networks. That's where cooperative coevolution comes into play. What cooperative coevolution does not come into play is the fact that my entire problem is highly interlinked to each other. There are no independent components. And if there are no independent components, then what will I do? So those were the problems that we looked into, where changing out even a gene by little value could sufficiently affect the entire individual. So those are problems where even a small change somewhere can destabilize everything up. And because it can destabilize everything up, those are not the solutions which could potentially be solved by using a cooperative co-evolution. However, things like you want to make a team, good football players, so the selectors do the initial thing that, okay, you are responsible for this thing primarily, you can show some cooperation there. Then the training of all the players could even be independent. Everybody knows the duties and responsibilities and what the other expects out of you. So, above all, summarizing, in a cooperative coevolution, all that I do is that I say my problem is a ecosystem, and the ecosystem consists of multiple species, each representing a sub-problem, but I cannot have random solutions to each species. I cannot have independent evolution of each species. The species cooperate with each other. So the entire problem was, what do I give a fitness function value to a particular species? And that's a problem that I solved by saying that a species will be given an immensely high fitness function value. A species will be called as good, not because it looks good to me, or not because it's doing something great, but because its contribution to the entire ecosystem makes a high fitness function value of the entire ecosystem. And to calculate the fitness function of the entire ecosystem, we placed it with a group of representatives, saw how it interacted with each other, what was the fitness value of the overall ecosystem. That became the fitness function value. But then, of course, the problem was, how do I get representatives? I cannot use all the individuals and see all the interactions. So how do I get the representative? And that was solved in a master-slave fashion, wherein the master combinatorial optimization problem provided good permutations and combinations of individual of different species to say, yes, these are good individuals. Those were given as representative to the slave, and the slave calculated its fitness function value based on that. It also calculated its fitness function value based on whichever individuals of the ecosystem of the master population it's a part of, how good are they performing. And in turn, the master combinatorial optimization problem solved a combinatorial optimization problem for the slave. So it was basically responsible for getting the slave individuals. It was basically responsible of getting the correct combination from the slave individual. It itself did not optimize the genes that the slave was doing. It itself only used the genes optimized by the slave individual to get the correct combinatorial optimization problem solved. And using this, we imitated how different species in an ecosystem cooperate with each other. And we use the same in order to evolve or to solve an optimization problem by breaking in one big problem into multiple sub-problems called as species, which potentially appeared to be independent of each other.